All right, folks, let's talk about reversible reactions and dynamic equilibrium. There is a thermochemical component to this topic, but we're not going to address it right away. We need to have a sense of what these things mean before we start introducing the energy component into these two things. And so it does belong in the thermochemistry unit, but we're just not going to talk about energy transfer here just yet. So let's just get to know what these terms mean. First, reversible reactions. So most of the reactions we've talked about in class so far this year have just been one-way reactions. Like picture this paper if it caught on fire. You know, paper is basically a carbohydrate. It's made of cellulose for the most part, which is got carbon, hydrogen, and oxygen in it. And when you burn paper, you're releasing carbon dioxide, water vapor, and it's, you know, next to it is impossible to get that to go in reverse. We can't take a burned paper and do something to it to make it back into unburned paper. And so that's a one-way reaction, but lots of reactions are not one-way like that. So here's really how we define a reversible reaction. The products of the reaction can then reform back into the reactants that they were originally produced from. And it's really hard to just pull examples of this out of thin air. You kind of got to know a few of these, but it's pretty interesting. So you think about like the products becoming, or excuse me, the reactants becoming the products, and then the products forming back into the reactants. That's a reversible reaction. So let's take this one as an example. This is ammonium chloride, and it decomposes into hydrochloric acid and ammonia. Okay, and so there's a really interesting little lab demonstration that we would have done here, where we take this solid ammonium chloride, which is this kind of white crystally sort of powder stuff, and you put it in a test tube, and then you put some heat underneath it, and the heat causes this chemical to decompose. And there are ways, and you know, you don't know your acid and base chemistry just yet, but there's ways we can determine that hydrochloric acid as a vapor is coming out of here. And there's also this stuff, ammonia, which is coming out of here. Okay, and yeah, you can hold what are called indicator papers above the mouth of this test tube, and you can see that there's an acid coming out and a base coming out. So there's really an interesting chemical reaction that's taking place here. But over time, once you let this test tube cool off, here's the cooled off test tube, and there's still a big chunk of ammonium chloride down here. But you can see along the mouth of the rim here, and kind of inside here, the inside of the tube, there's this white crystally sort of powdery stuff that has formed on the sides of the inside of the test tube, and that is the reformation of ammonium chloride from these products HCl and NH3. So it's really interesting. And you know, where does that stuff come from? Well, it's the HCl combining again with the NH3 to make NH4Cl. Okay, so the ammonium chloride is being reformed from the products of the decomposition of ammonium chloride. So it's kind of interesting. And when that happens, we write the reaction a little bit differently. It ends up looking like this with these two arrows. And the arrow that we're most familiar with, we call the forward reaction arrow. And then we have the backwards reaction arrow. So it just signifies the reactants, which are always on the left-hand side, becoming the products, which are always on the right-hand side, and then these products reforming back into the original reactant, okay? Which is pretty interesting. So the way that this happens is that initially, when we have our ammonium chloride and when we first start putting the heat underneath it, that forward reaction takes place very, very fast. And you know, it's just producing, there's loads of this stuff, and then it produces a little bit of this stuff at a time. And the reaction rates back and forth are different. Initially there's really none of this stuff available to react back into a reactant, right? And so once we get a buildup of these things, the rate of reaction from product back into reactant can begin to speed up. And over time, the reverse reaction begins to increase in rate, and eventually the rate of the forward and reverse reaction will even out, and the concentration of the products and the reactions will not change. That's not to say that there's equal amounts of both reactant and product, but just the rate of change is the same. And so that is known as dynamic equilibrium, and that is oftentimes a pretty tough topic for kids. So let's explore that in a little bit more detail. And I've set up this elaborate demonstration for you. Okay, these hex nuts represent maybe a chemical that is going to change into something else. And so let's just say that the idea is to move these hex nuts over onto this side of the line. But this is a reversible reaction, and so you'll see what happens. So initially, these nuts begin to sort of drift over to the other side, and once there's a little bit of a buildup of these guys over here, as long as this is a reversible reaction under the right conditions, they can start to go back to the first side of the line. And over time, even though it might be a fast movement of these guys from left to right to begin with, eventually they'll start to kind of even out. And the best way to demonstrate this is just to think about the fact that, like, maybe as one nut comes over to the left, to the right, another one is coming back to the left. So one to the right, one to the left, one to the right, one to the left, one to the right, one to the left. And this is what we call dynamic equilibrium. We do see that the system is changing because we have movement of these things back and forth, but there's really no observable difference in the concentration of what's over here compared to what's over here, right? The concentration is not changing, even though, when you're just moving one back and forth, yeah, it's changing, but the end result is the same. Okay, so I hope that sort of makes it a little bit more clear. And another way to think about this is this kind of interesting example. Dynamic equilibrium can be found not only in chemical reactions, but in phase changes of certain compounds or elements or whatever. So this is a good example, bromine liquid. Okay, so bromine wants to usually be in a gaseous form, and so as long as we have this bromine gas sealed up in a flask with a stopper pushed in there tight, we can see something pretty cool happen. So as bromine begins to evaporate into its gaseous form, which it wants to do, right? It comes out of its liquid form into this gas that fills this portion of the flask up here. As the concentration of the bromine gas begins to increase, it will then begin to condense back into a liquid and fall back into the fluid down here. So you see kind of a reversible reaction. And over time, like if this was just sitting on the table in front of you, you wouldn't really see, you may know that there's bromine liquid and bromine gas, but you wouldn't see the flip-flop of these things, even though it is happening. But you can't observe it happening because it's in this state of what we call dynamic equilibrium. Also important, really important to know about equilibrium and dynamic equilibrium is that it must be a closed system. And that's because, of course, if we allow this bromine to just evaporate out of here and the stopper wasn't here, it would just go away, and eventually all of the forward rate, we could call it, like if we said basically bromine liquid going to bromine gas, let's call that the forward reaction. This rate would be really, really fast, and there would not find equilibrium if this stopper wasn't in place, because the gas would just, go out into the environment. So every dynamic equilibrium state must be in a closed system. There are ways we can manipulate these rates, and that is where we're going to start talking about the thermochemical component to this, and a concept called Le Chatelier's principle, but that is for another lesson, all right? So that is dynamic equilibrium.